Sir, we can start. Okay. Good morning to all the participants. So once again, I welcome you for this AICT sponsored national workshop on research challenges in advanced power converters for electrical engineering applications. And today our speaker is Dr. M. Prabhakar, who is working as a professor at School of Electrical Engineering from Vellore Institute of Technology, University, Chennai campus, Chennai. And he is going to deliver the lecture on the topic called high step up DC to DC converters. Now I'm very happy to share his profile, short biography. Dr. M. Prabhakar completed his BE in electrical engineering domain from University of Madras in the year 1998, and he obtained his ME degree with a specialization in the power electronics and drives from Bharatdasan University in the year 2000. During the year 2012, he completed his PhD from Anna University, Chennai in the area of resonant DC to DC converters. He has about 20 years of teaching experience at undergraduate and postgraduate levels, and he received the Outstanding Teacher Award for the year 2009. He was involved as a co-principal investigator and received seed fund worth rupees 3.4 lakhs, and he has delivered about 30 keynote addresses and technical talks at various seminars, conferences, and workshops. He is the reviewer for various international journals like IEEE Transactions on Industrial Electronics, IET Power Electronics, Renewable and Sustainable Energy Reviews, and International Transactions on Electrical Engineering Systems, etc. His area of interest include DC to DC converter topologies for DC microgrids and power converters for renewable energy applications. At present, he is working as a professor in the School of Electrical Engineering at VIT Chennai. Okay. On behalf of our participants as well as the management of New Horizon College of Engineering, sir, once again I welcome you for this national level workshop program. And now we can start giving the sessions.
Thank you, sir, for inviting me first and for that introduction. Good morning to all the participants. I hope everybody is safe, healthy, wherever you are. I'll now begin my presentation. Before that, with all your permission, I do not know whether recording is happening.
Yes, sir. Recording is happening.
Okay, fine. So no issues. All right. So I'll start my presentation. My presentation will be on high step-up DC to DC converters. In this lecture or in this talk, I'll be explaining the technical aspects. Along with that, the practical or experimental aspects alone. The theoretical part or the foundations, they are going to be only minimal, whereas I'll be sharing a lot of experimental results that have been captured while fabricating a converter. And my talk will be essentially based on these 4 references. They are quite recent references. In fact, 2 papers have been accepted and still only the proof has come. They have not yet been published or page numbers haven't been released yet. But because I wanted to keep the topic and the contents relevant to the modern day scenario, I have chosen these 4 references. Of course, along with this, whatever experiences I have gathered in the lab while conducting the experiments or while testing the converter, to be very precise, those experiences will be shared. Therefore, my talk over the next 1 hour or so will be on these aspects. As I said, the background aspect will be very, very limited. Whatever is required, that alone will be covered. It will not be dealing in detail with the theoretical aspects. Then comes the converter synthesis part, wherein the way we think about a converter or approach to arrive at a converter. What is the actual step-by-step procedure, or what is the thinking behind coming out with whatever converters that are going to be described over the 1 hour period. That will be dealt with. Then the practical design aspects. What are all the elements that are involved? What are the nuances that are required while we design practically and while we implement practically? those will be my main focus, because theoretical aspects, yes, somebody can get that knowledge, but practical aspect, I find it very rare, because over the previous 8 years or so, I have struggled a lot to get the required practical results and understand the power converter, the way they operate. Therefore, my focus is on the practical aspects along with the experimental results, and I will summarize the contents that have been covered so far. So to begin with, my talk is again going to start from the, as I said, the hardware aspects. Therefore, I will begin by showing a photograph of the first converter. This is just to give the participants a confidence that certain things can be done in lab. In fact, all the converter, all the elements used in this converter were procured from within India only. I had used Element 14, or online there is a website called element14.com. So all those components were procured from Element 14. The PCB was procured from Amazon. That's all. It is just a copper-clad PCB copper-clad PCB. Sorry, copper-clad FR4 PCB. With a glass epoxy layer. Therefore, we are able to see the tracks which will be beneath. This is again a single-sided PCB. Tracks will be on one side, the bottom side of the image, whereas components are going to be installed on the top. And these things are just text. So the PCB was fabricated in our own lab. We didn't go to any other place, or we didn't outsource the PCB fabrication, at least for the first two converters. This again, this is a whiteboard. Again, we procured this from Amazon. Any doubts? Any clarifications? Okay. Of course, I forgot to tell you. In case you have any doubts, please feel free to unmute and ask your query. Please feel free to interrupt. No issues. Now, this is again another PCB. This is again procured from Amazon. Same single-sided PCB. Again, components were from Element 14, whereas the next PCB was from this. We got it from, this is a double-sided version. We meticulously made sure that it looks professional in nature, because we had tested all those earlier. We had tested those two boards. They worked fine. So we got that confidence, but then we wanted to move to next level. We here means the team. These two students are, they are BTech students. They graduated just now in the year June 2020. And we, along with the team, myself and these two students, we just did this as a team. So we deliberated, and then we came out with, let's say, we'll go for a double-sided PCB that was affordable. In fact, the cost of this PCB is manageable. It was around $20 or so. That works out to roughly 1,600 rupees for 5 pieces, five boards, 5 pieces. They give a minimum of 5 boards, but the shipping charge was slightly more than the cost of the PCB. So the shipping charge was again around $25. Put together, it was $45. So we spent around 4,000 or 5,000 rupees for 5 boards. That was still manageable for us. No funding, nothing. Personal funding only. So, and this is the experimental test setup. Anyway, I'll be dealing with what equipments are required for obtaining the good results, or for obtaining the results and presenting them in a reputed journal. I will be explaining them. Still, just to again make things clear how they are arranged and other things. All these test setup, they are actually live. They were live when the photograph was captured. I am stressing this because even in some papers, I do find the photographs which are captured when things are not live, meaning the power supply will be off and everything will be in black color. That is not going to convey any meaning, any input, any information to the reader. So this is again another tip or another information which you can actually pick up. This is another advanced version, advanced converter also, advanced version of the converter also. The advancement lies in the use of a 4-channel MDO. Till that point in time, we had used only 4-channel DSO. I'll go to the previous slide so that you can understand the difference. This is a 4-channel DSO. This itself is a very good equipment, but the other one, MDO, stands for mixed domain oscilloscope. The advancement in this equipment is if you capture the waveforms, the spikes and other things, they will automatically be filtered mainly because of the capturing rate. They call it as sampling rate. Because it's an MDO, it samples at a very, I think it's 2 gigasample or 4 gigasamples per second. I'm not too sure. Probably you can zoom in and check that if needed. The model number is also given in this paper. So that is again a Tektronix 4-channel MDO. So these are the equipments that are required. I was talking about at the advancement. This is one advancement. Another advancement that we made in this converter was we captured the thermal image of the converter under working. The image is there under experimental results. When that slide comes, I'll tell you the significance of that thermal imaging device or thermal imaging camera or thermal image. So I'll throw more details on that. Now, so this is just the reference and a little bit detail about the practical aspects that are involved in the references. Now I'll start I'll start with a very brief background. So I may have to write something before, in case I bend down and look at the screen, kindly bear with me, because I may have to write down certain things as I was mentioning earlier. Now, all these converters, the high gain converters, which I'll be discussing, they are meant for photovoltaic applications. So we are seeing the photovoltaic panels, PV panels. Very broadly speaking, there are 2 ways of connecting. Everyone knows that. One is a series connected PV array, and in which many panels are going to be connected in series, and then they are net on net going to be connected in a DC bus. But there is a slight problem with regard to that series connected array, PV array. That problem happens when shading occurs. Let's say if some corners of the PV panels, they are shaded, then the output voltage from each panel that is going to come down. Therefore, the overall voltage which will be available, net voltage which is going to be available at the DC bus, comes down. So there are certain problems with the series connected configuration, mainly because of shading, problems due to shading. This is one main drawback of the series connected PV array. Another problem would be in case there is a fault. Let's say there is a fault in one of the panels. Obviously, in a series configuration, the entire string is going to fail. So under fault condition, the entire string fails. That is another issue with series connected PV array. Due to faults, the entire string fails. This is another issue which we need to remember, which means the DC bus voltage will go down to 0 because of fault, and there won't be any other supporting mechanisms. That's our assumption. There could be a battery arrangement, there could be another backup as well, but those things are going to be common for all systems. Here the objective is, how do we make sure that our high step-up DC to DC converters are useful, or what is the role of high step-up DC to DC converters in a PV system? That is the main objective. That's what we are trying to understand. All right. So the next arrangement could be parallel connected PV configurations, wherein we have many panels connected in parallel, and then that forms a DC bus. Quite obviously, the voltage at the DC bus is going to be same as the voltage of the PV panel because it's a parallel connected configuration. Voltage is same as the PV panel voltage. Understandably, the PV panel voltage is going to be very low. This will be of the order of, it starts from 12 volts and then you can actually find panels as high as 72 volts or 60 volts or 96 volts also. But beyond that, if you need, then the panel size is going to be huge. And it will be as big as a door or other things, depending on the power rating. Also, the size of the PV panel is also going to increase depending on the voltage level and the power level. So when the load is demanding huge power of the order of 500 watts or more, then the size of the PV panel at a higher voltage will be bigger. That again everybody can understand. Now the question is, what is the voltage level that one needs to provide the load? People have tried various DC voltage levels. Among various DC voltage levels, 380 volt or 400 volts, this voltage level is found to be more efficient, and this voltage level is used in data centers. It is again DC, it's not AC, DC. So data centers use 400 volt or 300 volt DC bus. And if you can recollect, the single phase inverter or single phase grid, inverter I'll reserve for at a later time, single phase AC grid, then the single phase AC voltage is going to be 230 volt AC, at least in India. Therefore, considering the DC bus voltage level, considering the modulation index, considering that somebody employs sinusoidal PWM and with a filter, with a modulation ratio, then 380 volt DC bus is required. Or in other words, the inverter is going to operate from 380 volt DC. Then the inverters will be switched using sinusoidal PWM. There will be a filter and there will be a grid control mechanism, so that 230 volt AC can be injected into the grid at the required power level. Therefore, the 380 volt DC bus, or to be for easier understanding, we can take it to be 400 volts also, because both are going to be same and they don't make much of a difference. That is what is required. Now the PV panel voltage level ranges from 12 volts to 60 volts, is very high actually, 12 volts to 60 volts. So from this voltage range, we need to think about 380. So 380 volt, please have it in mind over the next 30-40 minutes. There are other standard DC voltage levels. They are 48 volt, 120, 48 volt, 42 volt was actually used in automobiles. So this 48 volt is used in telecom applications, telecommunications. And 42 volt DC bus is also another bus which is used in, which was tried. I'm not too sure about the state of affairs now. The electrical system in vehicles. And 120 volt DC, that's another level, 230 volt and 325 volt DC levels. These are DC voltage levels, standard DC voltage levels that one could look up to. Obviously, depending on the power level, the voltage value, higher the voltage, it's better for ease of use. Now, our objective right now is to step up this 12 volt, or the low voltage PV input has to be stepped up to the required DC voltage level. So the main objective now is to step up the low voltage PV input. This must be stepped up, or effectively we are looking at 380 volt from somewhere close to 12 volts to, I'll write 48 volts. So from 12 volts to 48 volts, we need to step it up to 380 volts. Therefore, the voltage gain that we are looking at is going to be somewhere around this voltage. 380 volt divided by, if I take 46 for mathematical simplicity, it should be more than 10. So this is the voltage gain that we are looking at. We are trying to achieve that voltage gain. So this is where we stand right now. Now, what are the options before us? One easiest way is to use a transformer and step up. Don't worry, don't think that transformers don't work in DC. Yes, they don't work in DC perfect, but this is a switching transformer, which is mainly used for getting the voltage gain and decoupling the input from the output, primary and secondary, or isolation transformer. So isolated topologies essentially mean using transformers, something like a flyback transformer or a forward transformer using transformers. That is the meaning of isolated topologies. But there are certain drawbacks. Yes, this is one school of thought. The drawback lies in the high circuit breaking capacity, because transformers we can actually manufacture any transformer with quite literally any voltage conversion ratio or any turns ratio. Getting a voltage gain of more than 10 is going to be easy when we use a transformer. That's what we would think so. But the circuit breaker, especially at the low voltage side, has to be of very high current rating. So that is a drawback. Another school of thought would be never use a transformer. Instead, use the elements that are there in the circuit and try to come out with a voltage gain of more than 10. That is our requirement. When we use such an arrangement, any doubt from any participant? Should I stop?
No, sir. You can continue.
Continue. Okay, fine. So when we don't use a transformer, such topologies are called as non-isolated topologies. The advantage in non-isolated topology is because of the elements that are used, we get additional flexibility. Even if we use a transformer for isolation, the size is going to be reduced. This is again an advantage. Earlier circuit breakers, their current rating was higher. That was the drawback, but now that will be overcome. Biggest problem is going to be large DC currents. How do we interrupt those DC currents? That is a big drawback. Not a drawback, actually, it's a huge challenge. But there is light at the end of the tunnel. There are circuit breakers with 1000 ampere breaking capacity. Commercially available circuit breakers, they are again commercially available. Circuit breakers with 1000 ampere rupturing capacity, breaking capacity, they are available. I think the voltage rating is around 1.1 kV DC. So all these are DC circuit breakers. So it is available, which means now people can think about handling the power in DC form with that voltage level at that current rating. So totally put together, it will be around 1 megawatt, I hope. Yeah. So one individual circuit breaker can handle that much power. It is possible nowadays. Therefore, my focus is on only non-isolated topologies. Isolated topologies I haven't done, and I haven't. Therefore, I have not put up in that in my presentation. Now, to synthesize a converter, we need to understand from the basics. Therefore, we constructed, as I said, that this talk will be on practical aspects. So I'll be projecting only the practical details. Very briefly, what is happening in a classical boost converter? We want a voltage gain of, always remember this, at least for the next 1 hour, you try to remember this. The gain that is required is more than 10, which means V0 by Vin should be more than 10. This is our requirement over the next 30-40 minutes. Will a classical boost converter be able to give the required voltage gain? That is the question before us. The answer is no, but that has to be practically validated so that we understand what the problems are, and then we can proceed further. Or only when we understand the problem, we will be able to provide a solution, think about a solution, and synthesize a good converter. Therefore, we constructed a 24 volt to 48 volt classical boost converter, and then we tested, these are the specifications. We tested the converter. 24, this is the input voltage. This is 24 volts, fine, fair enough. This is output voltage. This is 46.9 volts. Remaining 1.1 volt gets dropped across the diode. So we have a diode here. So this is fine. The duty ratio can be computed from this. Duty ratio is actually D. First time, therefore I will write here. I do not know the specialization. Duty ratio D will be given by on time divided by total time. So this will be approximately 0.5. So this is fine as long as it works within this range where the voltage gain is 2, it's fine for us. But we deliberately increase the duty ratio. If you try to compare the duty ratio or compute the duty ratio from this, it will be close to 0.83 or 83% of the time the switch will be on. This waveform represents voltage across the switch. This blue color waveform represents current through the switch, and the green color waveform represents current through the diode. This is for our understanding. Suppose we want a gain of 10. Just to recollect quickly, V0 by Vin in case of a boost converter is given by 1 by 1 minus D. Therefore, if D equal to 0.8, then gain will be equal to 10. So we wanted to test whether the classical boost converter can give us that gain. That is why we chose the duty ratio as 0.835. But no, it failed miserably. Reason is, you look into the operation of the classical boost converter, then you will find that when the switch is turned on, the diode will be off. When the switch is turned off, diode will be on, which means the switch and diode, they must be complementary to one another. Both must not conduct at the same time. Switch and diode, I will write it as S and D, they must be complementary. Both must not conduct at the same time. That's the meaning of complementary. But at D equal to 0.835, here the current is non-zero, which means when the switch is turned off, the diode has already begun to conduct. Therefore, there is a portion significant duration during which both the diode and the switch conduct simultaneously. So that is the problem. Voltage waveform IL, which is ripple. So for PV application, if we have the ripple, when the current through the input, remember inductor current is same as the input current as well in a classical boost converter. So when we have an undulating current waveform, tracking the maximum point and implementing MPPT algorithms will be difficult if we have higher ripple content in the input current. This is another problem. So there are two issues now. One is the extreme duty ratio problem. Another one is the ripple content in the current, ripple current. I'll just put it as ripple current, you understand. These are the two issues in a classical boost converter. These are the problems. We have understood them now. I presume that we have understood them now. Next comes, how do we overcome them? Voltage gain obviously is limited. Extreme duty ratio leads to these problems. This or this. Okay, so power capability is also limited because you can't pump in more energy from the input to the output. Now, how do we overcome them? First, we'll take input current ripple. This actually leads to the converter synthesis. The method of overcoming these issues will give the converter synthesis part, how we are able to synthesize the converter. Fine. Okay, now we overcome the current ripple by using interleaving technique. The concept of interleaving is, supposing we have one brick, one block of a boost converter, or we presume that the boost converter is one brick. Then we can have one more brick in parallel. And we can connect the input and the load to those bricks. Similarly, we can have n number of sandwiches, n number of bricks, n number of blocks. This is the concept of interleaving. The advantage is one block, each block of boost converter is going to carry, let's say, a current I. Then when we have 10 such blocks in parallel, current is going to be shared by all the devices. The switches and diodes, current rating will be minimized because each parallel block is going to share the total current. But you are ready, you are happy with the current rating, but then you want to pump in more power, then yes. Let's say the switch rating is 1 ampere, diode rating is 1 ampere, then use 10 such blocks, then 10 ampere can flow from the input. But switch current rating especially remains only at 1 ampere. So power rating increases. All right, so these are the advantages of interleaving. Now, what is the main point that we were trying to address? The ripple content. That was the main point. Are we able to achieve or nullify the ripple content? We will try to understand. Now, we are seeing two such blocks. A two-phase interleaved converter is what is shown here. Two-phase, I will abbreviate this and write it as two-phase IBC. Interleaved boost converter. IBC represents interleaved boost converter. Now, if I operate S1 and S2 with a phase shift of 180 degrees, meaning complement to one another, then the currents IL1 and IL2, they will be complement or phase shifted by 180 degrees, and they will look like this. Suppose I turn on S1, current through this inductor L1 will rise gradually in a linear manner. At the same time, S2 is going to be off, therefore IL2 will decrease. In this manner, net on net, what is happening at this node? In is given by in will be IL1 plus IL2. Therefore, if I sum up those two currents, ideally it should be zero, meaning the ripple content should be zero. Total current will be sum of the average currents. That is what the interleaved operation, phase shifted interleaved operation, communicates to us. Fine. Now, this is actually a mouth-watering approach. Therefore, if we use n number of interleaved phases, then we will get a perfectly smooth DC current. Then everything is going to be fine. But is that a fair proposition? The answer is no, because we must limit the number of interleaved phases to 3, practically because the switch utility comes down. Supposing you have 3 switches or you use the 3-phase IBC, then each switch is going to conduct for 360 by 3, which will be 120 degrees. In case you use 6 switches, then each switch will just be conducting for only 1/6 of the time period or 60 degrees, which means you are not utilizing the switch completely, utilizing the rating of the switch completely. So that is another drawback. Therefore, practically we limit it to 3. But it's not a hard and fast rule. There are 4-phase, 6-phase IBCs also. Or let's say you take two-phase IBCs, connect those two phases in parallel, then that's fine. That's fair enough. So, but generally, this is an overall perspective. You limit the number of IBC phases to 3. Fair enough. Theoretically, okay. But is it going to work in reality? Therefore, we again tested, constructed a 2-phase IBC, same voltage gain. We haven't changed the voltage gain. Voltage gain is going to be 4824, which is 2. But now the power level, this has doubled. Earlier it was only 48 watts. Now it is 96 watts. And these are the actual waveforms. IL1, this is IL2. And look at this wonderful waveform. This is the input current, IN. Perfect, smooth, ripple-free input current. Ripple-free input. Absolutely fine. You see only these glitches because those are the instants at which switching happens. Switching from S1 to S2 and the other way around. Or current gets transferred from one phase to another phase. Other than this, it's perfect constant. That is validated by this ripple content also. Earlier, if you could remember, for 4 ampere input current, the ripple was 1 ampere, 1.04 to be precise. Whereas the total current is now again for 2.13 plus 2.20. The sharing of current has taken place. Totally, it will be 4.33. So current input current is shared, but the ripple content, this is delta IL. This is negligible. It's just 0.48 amperes or 480 milliamperes. This is the beauty of interleaving. So what is the green shoot? The green shoot is ripple content has come down. Ripple is reduced. Okay, so I have written here, fine. So ripple is reduced. Not even reduced, actually nullified. If you use a good interleaved converter with good proper gating sequence, it will be nullified. But what about the gain? Gain is only 2, 23.9 to 48. Voltage gain, I will now denote it as M, voltage gain. This is only 2. So as we see here, gain has not increased, only the ripple content has come down. Only the ripple is reduced. Delta I. This has been reduced using interleaving technique. So still we are left with one more issue. That issue is gain extension. We will attack that. Okay, so we'll look at that. These are few methods. One is using a coupled inductor and then voltage lift capacitor, BMC and DC.
I don't know how it will be on one.
What, was that a question? Should I? Was there a question from any participant? Can I carry on?
Yes, sir, you can carry.
I can. Okay, fine, no issues. So these are some of the gain extension mechanisms which have been used to enhance the voltage gain. Remember, we need a voltage gain of minimum 10 with reduced ripple at reasonable power rating. These are the issues before us. From the classical boost converter, the extension is what is shown over here. This is actually called as a quadratic boost converter, QBC, quadratic boost converter, abbreviated as QBC. Quite obviously, V in L1, D1, C1, this forms one boost stage. So this will be one boost stage, and C1 will act as input to the next boost stage. Right? So that is the way QBC operates. The voltage gain V0 by Vn is going to be given by 1 by 1 minus d for the first stage multiplied by 1 by 1 minus d for the subsequent stage. So net on net, it will be 1 by 1 minus d, the whole squared, where d is, just to recollect, is the duty ratio, which will be on time divided by total time. So this is the principle of QBC, quadratic boost converter. Now, using a quadratic boost converter at, let's say, a duty ratio of 0.5, the gain would be 1 by 0.5, which will be 4 times. So gain will be 4, 0.5 squared, sorry, I miswrote that square, 0.5 square, that will be 4. Right? Whereas in a classical boost converter with a gain, with a duty ratio of 0.5, gain will just be 2. Now it is doubled, quadratic. This was again very, very attractive for us. Therefore, we constructed an advanced version. I have to erase certain things. I will do that now so that it becomes clear to you. At least the circuit which is shown in this slide is clear to you. Yeah, I hope it's clear now. Now, we had very casually, we had a discussion on QBC, and then we were discussing its drawbacks, because when we had written our earlier journal paper, we mentioned that QBC has some disadvantages. Therefore, we didn't want to beat it down to death. And then we thought we can just work on a QBC. The drawback is S1 and S2. The switches which are used, they will be subjected to very high voltage stress. That is the main drawback of QBC, because they are located very close to, I'll go to the previous slide so that you will understand better. See, S1 is located closer to the output voltage, closer to the load terminal. So voltage stress on S1 will be same as the output voltage. That is a very, very big drawback. This was the drawback which we had pointed out when writing the introductory part in our earlier journal. So we thought, why should we keep it like that? Why not reduce that? And then we thought of cascading 2 QBC structures and then coming out with one converter. And those 2 QBC structures, as you can see, are indicated as QBC1. This is the first QBC structure, and QBC2 will be the second QBC structure. So we had replicated 2 such QBC structures. This is again an interleaved version, but instead of grounding, we had simply connected the output of first QBC through a lift capacitor. This lift capacitor is indicated as C lift. This technique is called as voltage lift technique. So we simply lifted the voltage instead of grounding. We simply lifted that voltage and then had the energy stored in a lift capacitor C lift. This was our idea. Now, very easily, quite easily, the voltage gain at this node will be 1 by 1 minus d square. Because this is converter synthesis, I am explaining these things. More details can be found from this journal paper. You can download this, or if you need, my mail ID is here. You can just mail me. Mail ID is there in all slides. In case you are interested, you just mail me. I'll send you the paper. No issues. Fine. So this node will be at a voltage level of 1 by 1 minus d square. Another QBC again will give us 1 by 1 minus d square. They are cascaded. They are added. One is getting added to the other. Therefore, at this node, with respect to ground, we will be getting a voltage of 2 by 1 minus d, the whole square. So the voltage gain of this QBC structure, interleaved QBC structure, is going to be M. I will name this as IQBC. Interleaved QBC structure will be 2 by 1 minus d, the whole square. Therefore, if we operate at a duty ratio of 0.5, now our gain will be 8. It's not 4 anymore, it's 8. All right. So significantly increased. But what will happen at input current? It is interleaved configuration, D0.5 ripple will be 0. So those are the things that we wanted to verify. So one modification, one novelty is this voltage lift technique. There is another novelty, that is, instead of having discrete inductors, L1 and L2, they should be discrete in a class. They are generally discrete. Discrete meaning separate components. You will have L1 as a separate component, L2 as a separate component. But we didn't do that. We used a coupled inductor. L1, L2 is coupled. L1, L2. This is coupled. So L1, L2 will form the first Ci, which I name as Ci1. They are wound on the same core. Similarly, L3, L4, they are wound on the same core. Similarly, L3, L4, they form the second coupled inductor. Fine. So instead of using 4 separate elements, we used only 2 coupled inductors. That's the second novelty. 2 coupled inductors. This is what we used. Therefore, the advantage is circuit becomes compact because you don't need to arrange 4 inductors. It's very easy for you to handle 2 components rather than 4 components. So this is the, remember this was the first photograph which was shown, first reference. Of course, these are the specifications. So 24 to 380, this will be a voltage gain of 15.833. This is our requirement. We tested at 100 watts. D was slightly higher. D is slightly higher because at 0.5, as I was mentioning earlier, voltage gain will just be voltage gain will just be 8. Therefore, whereas we need a gain of 15.83, therefore duty ratio must be increased. Remember, coupled inductor, they are not providing any voltage gain. Turns ratio we are not using for gain. They are simply used for L1 and L2 only. But other operating principles, we just wanted to confirm. Voltage gain, that is confirmed. We are getting 376 volt from 24 volt input. That's fine, fair enough. Very close to our requirement. Acceptable. Acceptable by standards, not because I have done this. There is one IEEE standard. You have IEEE 1547 interconnection standard. So based on that standard, voltage regulation can be 5%. So plus or minus 5% of B0 is permitted. That is one of the reasons why we fix the output voltage plus or minus 5%, because that regulation is permits us. Fine. And then these are the inductor currents. I will name them as I1, I1, I2. This is the input current, I in. Remember, duty ratio is 0.65. It's not 0.5 anymore. It's slightly higher. Therefore, there is ripple content that has to be kept in mind. Delta I is slightly on the higher side, unlike the classical IBC, which operates at 0.5 duty ratio. That was a perfect constant ripple-free input current. Here, because D is 0.65, there are undulations. There are undulations. I am referring to these things. Okay, so it switches back and forth. There are ripples. Okay. Switch stress. Earlier I said the switch is located very close to the output voltage. It will be same as output voltage, but here, because of the voltage lift technique, look at the stress, it's only half, 184 out of 380. So it's only half because of voltage lift technique. So we managed to bring down the voltage stress on the switch by one half. Those are the advantages. These are, of course, meant for the user or meant for the listeners, participants. These are actually diode waveforms. Waveforms across, I will name this as voltage across diode D1. I will point out diode D1 here, D2 here. Right. So remember, all the diode voltages, they must be negative. So when the diode is on, this is the duration when the diode is on. When the diode is off, it must block a negative voltage, reverse voltage. So when you capture, please capture it properly. This is the voltage across the switch S1. And try to see the correlation here. When switch is on, D1 will be off, D2 will be on, something like that. So that when you refer to the operating principle, it will be perfect. That has to be, this is called as correlation. This is the way you have to capture the experimental result. This is again a tip. I know that all are professors, but still, I just wanted to share my experience, which is very hard because I rarely find good papers for review also, wherein all the information is available. But I am sure these participants and these professors will gain by looking at these waveforms. So this is one thing. Another thing is they must be compared with the output voltage. So this is the way we had used all the 4 channels. And compared to the output voltage, this will switch stress will be half, diode stress will be even reduced. It depends on the location of the diodes. That can be traced. Once you read the paper, you will be able to understand. So this is the way experimental results have to be captured and projected while writing a journal paper. This is for the next QBC structure. QBC2, we have other set of diodes, D3, D4, D interleaved. So they are the waveforms for those diodes also. This is the next switch, another switch. Again, please take care of the correlation. How do we correlate the circuit operation and how do we substantiate the circuit operation through experimental results? This is the take-home message from these waveforms. All right. I will pause for, I think I have spoken for 45 minutes. Can I pause for a couple of minutes? If there are any questions, can I take them and then proceed further?
Good morning, sir.
Good morning.
Hello. Sir, you have designed that total converter and that input output, how you decide, sir? Means for this converter, this much of voltage I will take. This design concept, sir, can you just
got
share?
it, ma'am. Yeah, any other question, ma'am, or can I answer this question?
Yes, sir, you can answer.
Okay. Yeah, I will answer this. The standard output voltage has to be kept in mind. The output voltage must be fixed first. Therefore, output voltage is 380 volts. So that output voltage is fixed. Input voltage is decided based on the PV panel availability. Of course, in our lab, we have 18 volt PV panel, but the power rating of that PV panel is less. Therefore, depending on the input voltage, again, the input current is also going to be slightly higher if you choose a 18 volt. Therefore, just to have a let's say a middle ground, we slightly increase the input voltage to 24. So first we fix the output voltage, that is 380 volt standard. And then the input voltage we fixed based on the availability. Of course, we didn't test it using a PV panel. We tested only using a DC supply, but it will be close to the PV panel behavior, right? That is the way we fix the input and output voltage.
Okay, sir.
Fine. Any other question?
Sir, the participant raised a question. What is the lift rating in QBC?
Lift rating in
QBC. Yeah.
Okay, fine. I'll go back to the previous slide and then I'll explain.
Yes.
I presume that the voltage rating of this C lift is what the participant is trying to ask. The answer is the power rating that is handled by the entire converter. That has to be the rating of the capacitor. Of course, capacitor, we don't have power, we have energy. We can correlate energy power. So that is the way we fix the rating of the lift capacitor.
Sir, another question. Do
Yes,
we need to keep some dead time between interleaved converter switching of both devices?
Not required, sir.
Okay, sir. You can continue.
In fact, that time in this waveform, both devices conduct at the same time. For some small duration of time, both devices conduct. If the participant can observe, this is one, this is another. So during this small time duration, both switches conduct at the same time. Nothing is going to happen. As long as both switches conduct, nothing. Switch and diode in one boost cell or in one QBC cell, if they conduct, then problem. Problem with regards to energy transfer, power transfer from the input to the output. Then only there is a problem. Okay, fine. Any other questions or can I proceed further?
You can proceed.
I can proceed. Fine. I'll move to the next converter. Okay, so this is not yet over. Fine. Now this is actually the voltage regulation characteristics of the two-phase IBC, where the first waveform on the left shows the load current being maintained a constant. Input voltage, I was mentioning to one of the participants answer that it will resemble the PV panel behavior. Therefore, we varied the input voltage. Look at these variations, 20.9. So the range of variation was 20.9 to 27.8, which means you can roughly assume 21 to 28 volts was the input voltage variation. But the output voltage remains fairly a constant. Yes, you do see a dip, you do see a peak overshoot, but they are within that 5% norm, IEEE 1547 standard. But they settle down very quickly. We didn't use any complicated control, no neural networks, no artificial intelligence, nothing. Simple proportional integral proportional controller for this converter, that's all. Simply we adjusted the gain. In fact, we used only a lookup table sort of a search for this control mechanism. We did not use AI, we did not use neural networks, not needed actually. Again, the participants, if you are open-minded, you may accept, but if you are doing your research in AI, then you would claim that AI is excellent. I may have to accept that also. Fine, there are different schools of thought, that's all. So this is load regulation, where I will write this as line regulation, and I will write this as load regulation, where the load was also varied. We had a rheostat and then we varied that abruptly. Look at this abrupt change. These things occur practically. Therefore, we changed the load. And remember, input voltage was fixed. Just see the output voltage, perfect constant straight line from 198 milliamperes to 304 milliamperes. 275 is the nominal current. normal load current at 100 watts. So 304 will be slightly over that 100 watt behavior. So this is the efficiency part. Efficiency was close to 93%. That's what I remember. The exact value is given in our paper. I don't remember. Anybody can compute from this. This is V in, this is I in, this is I naught, this is V naught. So you can compute that and you can find out for yourself. It will be close to 93%. That's again acceptable. For this is now again just a word of caution, not for industrial standard. Industries may need 99%, but academic research for domestic application, for DC microgrid application, yes, you can interconnect, you can use this converter, not an issue, because the regulation characteristics are fine. Efficiency is 93%. With some protective mechanisms, you can use this exact converter for DC microgrid application. So that is the first converter for you. Second converter is an advanced version. First converter was still this. Stage 1 was an IQBC with C lift. This was the first converter. Second converter, already we had used a coupled inductor. So our thought was, why not have one more winding on the coupled inductor and connect a voltage multiplier cell? That was the idea. Therefore, we implemented this. Stage 2, we had used voltage multiplier cell. VMC stands for voltage multiplier cell. The advantage of this is, till C lift, the voltage gain will be 2 by 1 minus D square. Because we have used two coupled inductors, we will now have the turns ratio also as the gain factor. Of course, for practicality, we will put K also, where N is the turns ratio, small k is the coupling coefficient. Practically, you will not have 100% energy transfer from the primary to the secondary. Here, primary, secondary, tertiary. So from the primary to the tertiary. Therefore, there will be some sort of leakage coefficient. So that is called as coupling coefficient. So this is the practical voltage gain for this converter. This is the additional gain. Remember now, turns ratio we can adjust. We can just play with that turns ratio and then we can get very good values of voltage gain. Number one. Number two, because we are using coupled inductors, just like they are similar to transformers, more amount of power also could be transferred. So we tried this converter. Now look at the input voltage, 18 to 380. The voltage gain will be around 21.11 times. 380 by 18. Right? Power rating, earlier it was 100 watts, now it is 150 watts. 50% more, sorry, 50 watts more. Duty ratio, we have brought it down. Earlier it was 0.65, now it is 0.5. Frequency, earlier it was 40 kilohertz, previous converter, now it is 50 kilohertz. So advanced version of the previous converter compared to the interleaved converter. Results are shown over here. They will look exactly similar. Voltage gain confirmation from this, duty ratio confirmation from this. And I always like this waveform wherever I see such waveforms. Input current, ripple free input current. No ripples at all, absolutely constant, wonderful ripple. Current sharing mechanisms. This will be I1. I will name this as I2. Look at this current. Of course, here this is with ripple, this is with ripple. So current is going to be equally shared among the interleaved phases. Because of this 0.5 duty ratio, ripple is reduced. Absolutely no ripple at all. And as always, the load regulation and line regulation characteristics. Again, perfect. Output voltage is constant at 380 with very small tolerable dips. When load changes, nothing happens to the output voltage. Perfectly constant. All right. So this is the second converter, which is again an advanced QBC version. We didn't stop there. We were slightly greedy, to be very frank with you. So actually, I got this idea when I was driving back home. And then next day I went and then I told Vijay, Vijay, why not have 1 by 1 minus d cube or 2 by 1 minus d cube? Why not have, why should we stop with cascaded or quadratic boost converter? Why not have cubic boost converter? Cubic boost. This was the term which popped out from my mouth. Cubic boost converter. Or a converter with 1 by 1 minus d power 3. Why not think about such a converter? And then we came out with this idea. Till this point, it's going to be 2 by 1 minus d square. This point. This we have come across. Sorry, this is actually a boost converter lifted. So till this point, we will have across C1, we will have 2 by 1 minus d. And then we had another QBC structure here. So 2 by 1 minus d will be the input to the QBC. QBC we know gives a voltage gain of 1 by 1 minus d square. So it will be 2 by 1 minus d from stage 1 multiplied by 1 by 1 minus d the whole square from stage 2. Totally, this should give a voltage gain of 2 by 1 minus d power 3. This is cubic boost. So this was the question. We had twice the gain of a cubic boost converter. Fine. Fortunately, the title is also here, cubic voltage gain capability. And because the input is interleaved, it will always be constant. The input current will be constant and ripple free. Voltage gain will be excellent voltage gain characteristics. And because we are having two stages, we can use one stage for controlling the output voltage, for regulating the output voltage, another stage for maintaining ripple free input current. Meaning, first stage, if I name the duty ratio as D1, second stage, if I name as D2, I can use D1. I will strictly maintain this at 0.5 so that I get ripple free input, ripple free IM, input current. And if I vary D2, I can have voltage regulation characteristics, or I can vary the output voltage. This is the novel feature of this cubic voltage gain characteristics. Right? One duty ratio is used for fixing the ripple, eliminating the ripple rather. Another duty ratio is used for meeting the voltage gain requirement or voltage regulation profile. That's all. Will it work in practice? It did work in practice. Right? So this is the test setup, which was again shown as the third photograph. Again, test results. Test results are there in paper. I haven't put up them now because they will look similar. So you can refer to the paper and you can understand. Or as I said earlier, you can mail me. I will be glad to send you the version. That was my thought. But actually, this was my thought. I just said, why not have 2 by 1 minus d square? Of course, this converter will give 2 by 1 minus d the whole square. And then I told him, why not cascade with another boost so that you get 2 by 1 minus d cube. So here it is 2 by 1 minus d the whole squared multiplied by 1 by 1 minus d. This was my thought. This was my circuit. But Vijay suggested, sir, this circuit is meaningless because you have many components. So it may not work. That was his suggestion, and it was he who suggested the previous version. This circuit was suggested by Vijay. What he did was he simply changed. This comes under converter synthesis. So you should know how to arrange the components. Look at the first stage. This is QBC, two-phase IQBC, interleaved boost converter, two-phase IBC rather, two-phase IBC. Second stage is QBC. Fine. Whereas you interchange these two stages. Make stage 1 as QBC, stage 2 as CBC. That's my suggestion. Stage 1 is QBC, stage 2 is CBC. Still the voltage gain will be same, but component count will be higher in the second case. Right? He was a bit skeptical whether the circuit will work. Therefore, we actually simulated and not simulated. We didn't simulate. We actually rigged up this circuit. We tested this converter first. This converter only we did first, and then we presented, we published. Actually, Vijay was not in favor of doing this, but then I told her it's an idea, it's a converter. So let people know that this is another possibility. We did this converter. We again compared with our previous version also. That also we have done. To be very fair, we have done that also. So the speciality of this I told earlier. One is this MDO. I'll show the results. Another is the thermal image. I'll just project that thermal image. Now look at the waveforms. From the scale, you can actually read. Please do not cut all these scales. Do not crop and say that it's not fitting in the template. Nothing. Look at our journal. It's fitting up. Don't do anything. Don't write anything inside the waveform. Nothing like that. If you want, don't erase anything, any scale, dates. Let them be there. Nobody is going to question you. Put the date so that you will also know that you have done such a good work at particular time interval. So these are the waveforms. The voltage across these switches, they are captured without any spikes. You can actually understand when you compare with the previous waveform. Most important thing, yeah. Now this is input voltage varies. So this is line voltage regulation, line regulation characteristics. This is load regulation characteristics. Again, I reiterate, for this converter, we used PID controller, and the tuning was done by trial and error method only. We didn't use Ziegler-Nicholas, or we didn't use simulation, nothing. There used to be a filter. There will be a filter in the microcontroller, and then that filter, depending on the filter output, the KP, KI values were adjusted. That's all. That is the fact. Sorry?
Sir, continue.
Okay. Now, this is the thermal image of the converter. You can see the red spots. So, I mean, red, yellow, blue, everything is there. The temperature at each point is also mentioned over here. Maximum temperature was 71.4 degree, phased by the third switch. Third switch, I'll go to the previous slide and show. This is the third switch. Please remember, this switch is very close to the output. Therefore, the voltage stress on S3 will be same as V0. That is a drawback of this converter. But when you compare with the voltage rating of S1 and S2, S1 and S2, it will just be, in this case, it's in QBC structure, right? So it will be 1 by 1 minus V square. That's all. So it's very, very less. When you compare the voltage stress on S1 and S2, you can afford to have high voltage stress on S3. That is why it has been accepted by the reputed journal. Else they won't accept. Even if they find one, if they pick one. Of course, we do write that, yes, it is a drawback. We have mentioned that categorically, clearly. So the classical version, the normal photograph is this. For this, the thermal image is this. The reason why we capture this thermal image is we should know which part in the converter is getting heated up and whether it will be able to withstand that much amount of heat. That is the main reason why we capture this thermal image. For this, you need to have the thermal imaging camera from FLIR that we had, and we use this. That's all. So with that, I would like to just summarize certain things. With regards to the practical design aspects, one must, one of the participants also asked this question: how do you choose the ratings? First of all, choose the output voltage so that it meets the standard voltage level. And then you have to pick the switches with very low on-state voltage drops. Don't think that the devices will fail if you use tight ratings. What do I mean by tight rating? Suppose the voltage rating, the required voltage rating, design value works out to 50 volt. Choose a switch with 60 volt. That's all. In fact, we had used only such switches. We never gave huge safety factor, meaning suppose the voltage rating is 50, don't use a switch with 250 volts voltage rating. It is going to be a waste. In terms of cost, leave that. You may be rich, that's fine, leave that. But in terms of efficiency, in terms of your overall power rating of the elements used in your converter, it's not a good thing. If the voltage rating is 50, use 60, 65, that's all. But focus on this very low on-state drop. that has to be minimized. Very, very low. Only then you can get efficiencies in the high 90s or at least in the early 90s, 90 to 95, somewhere around that. Remember, all our converters, they worked in that range, 90, above 90. I'll put it that way, but they were actually above 92, I believe, 92 to 95, that was the range. Another thing, when you use diode, again, same thing, use low voltage diodes. This is where you may find a difficulty. Practically, it's very difficult to get good diodes with low forward voltage drop. In fact, we found out that there was one diode with 0.5 voltage drop across it. We used such diodes. They were expensive, but we used such diodes. And then with regards to the magnetic elements, very, very important thing, all are custom made components, meaning we wound the coupled inductors on our own. We wound the inductors on our own. We didn't outsource and then we didn't get it ready-made. We didn't do that. They were wound on our own. So choose the proper core and the air gap between the two cores, or air gap, that's all. That must be fixed. When you go for PCB, outsourcing PCB, you have to be very, very careful. Test points, current measurements. You must think or visualize how the PCB should be and where you want to take the measurements. Based on that, you have to allow the test points, or you have to provide all those test points. Similarly, track with wherever you need more current to flow, have a larger, wider track. The input output ports also, arrange them neatly. Technically, it is called as footprint. Okay, so choose components with standard footprints. That's about the practical design aspect. And when you capture your experimental results, please make sure that there is correlation. I was talking about this correlation earlier also. I had explained them, but this is again just a recap of whatever we have seen so far. DSO or MSO with proper current probes, they are important. Scale attenuation, they are again important, because I say this, I find it painful when I get papers for reviewing saying that 5 ampere flows, but then the scale says both as voltage. Both will be in voltage mode, but then the authors would mention current. And that is not painful. Actually, they might have calibrated it, or they might have used a current shunt, capture the voltage. They might have used that, but those things must be written clearly. Only then the reader will understand and start appreciating, learn something. So that is why I say these things. Use current probes, check the scale, proper attenuation scale. You take any of our waveforms in our papers, scale, everything will be perfect. The user can do in the reader, can do in his or her premise, make sure that the circuit works in their premise as well. Okay, so that sort of repeatability should be given to the reader. Microcontroller, of course, you have to use the ADC inbuilt, analog to digital converter. There is an ADC inbuilt. You have to use that judiciously for filtering out the noises, especially during feedback process while implementing the closed loop. Otherwise, we didn't do we didn't use any special equipment. No FPGA, no DSP processor, nothing. We simply used a STM Fire microcontroller that was used. It is there in our paper also. You can again take it and 1240. Okay. Loading arrangement, these are the essential things. So to summarize, as far as high step up DC-DC converters are concerned and DC is concerned, historically DC was the first form. All of us know the war of currents between AC and DC. And when we use electrical power in DC form, we will have certain advantages. Residential loads, VFDs, the internal AC-DC rectifier stage will not be there. We won't have any power quality issues. Therefore, we can easily work under DC condition also. Talking about the present day reality, renewable energy sources can easily be integrated into the DC bus. One need not struggle, invert it and then use them. Power converters, they are trying to make a mark and now they are trustworthy. Earlier they were not, but now they are becoming more and more reliable. So to conclude, it is better if AC and DC coexist, and there are more and more power converters which are in use for integrating the input DC to a common DC bus. On that note, I would like to thank all of you for the wonderful opportunity given to me, especially to Dr. Vinod Kumar for inviting me. If there are any other questions, I'll be glad to answer them.
Sir, the participants raised some few questions.
Yes, sir.
Are you considering the effect of parasitics in DC to DC converters?
Yes. In fact, the efficiency can be computed by considering the stray resistance of the inductor, leakage of the coupled inductor, the on-state resistance drop of the MOSFET, voltage drop of the diode. These are the main parasitics involved. Yes, we did consider them, and we have given a loss breakdown. Can I do I have time, sir? Yes. Sir, can I show something? 1 minute.
Yes, sir, you can show.
I can now. Yes. Very quickly, I'll take. Yes, I think this is what. So we had considered the loss in coupled inductors, loss in diodes, switching loss in switches. They do mean that the parasitics have been taken into account. I hope this answers your question. Next question, sir. Any other question?
You have used? Which controller you have used?
Sorry, sir. I missed out the first part of your question, sir.
Which controller
Okay.
you have used?
Okay, got that. I'll tell the controller. I remember, yeah, STM Fire. STM32, it's not Fire, sorry, the STM32F411RE.
Okay.
STM.
Okay, sir. Third question, how to select the inductor value that converter will operate both continuous conduction mode and discontinuous conduction mode?
We didn't consider DCM at all because for renewable energy application, only CCM is preferred. If you allow DCM, current from the PV panel, current drawn from the PV panel needs to go down to 0. That is not preferred. So we didn't consider DCM. All our converters were designed to operate only in continuous conduction mode, CCM.
Okay. Another question, which language is required for programming in STM microcontroller?
This they worked, I think he was working in, it was similar to C language, but I'm not exactly sure. It was similar to C language.
Okay. So another question, any comment on superlift Leo converter in comparison with the IBC?
In my, of course, I haven't fabricated a superlift Leo converter, but in my understanding of working with the other power converters, Leo converters are essentially based on capacitors, charging the capacitors and discharging them. Handling capacitor discharge will be a big deal because the switches and diodes, they are very fragile when heavy inrush current flows. Therefore, I just visualize that the superlift Leo converters may cause, I'm not too sure, I haven't done any practical experiments on them. So they may cause inrush current issues, meaning switches and diodes may fail frequently. That's my understanding. But I have to reiterate, third time I'm saying, I haven't done experiments on superlift Leo practically.
And what is the power MOSFET and diode you used?
Yes, I'll show them. So this is the power MOSFET. I hope you are able to see this. I'm still sharing my screen. Yes. Power MOSFET is 150 volt, 83, 12 milliohm. Fast recovery diodes, there are plenty of diodes. This is for one converter. Similarly, there are other converters also. Very quickly, I'll show them so that I can take up the next question. This is the power MOSFET of another converter. Power MOSFET and the diode. Power MOSFET and diode of the other converter. Similarly, there are 4 papers are here, so you can just see through them or browse through them for getting the switch and device ratings.
Okay, sir. So another question, in case of multi-port isolated DC to DC converters, which topology is most suitable for DC microgrid applications?
Absolutely clueless, sir. Reason being, you never have a particular converter called best converter. Of course, the participant I had asked most suitable, nothing like most suitable. And that too being isolated converters, you can actually fine tune the turns ratio, and then you can adjust the turns ratio to meet the requirements. So
okay.
That's the answer. Yes, sir.
Okay. Which control method is preferred in isolated DC to DC converters, whether it is phase shift or PWM control?
Is it with regards to DC converters?
Yeah, DC to DC converters.
DC to DC phase shift is one. What is the other one, sir?
PWM control.
PWM, I don't understand.
Maybe the question is wrong.
Okay, probably for inverters. So no, I haven't done much research on that.
Okay, sir. Okay. Another question, whether particularly suitable for high frequency compared to FPGA? Your experimental setup will be suitable for high frequency.
Definitely, because FPGA you can program at you can obtain the gate pulse at megahertz, kilohertz. We had done only till 50K and 100K. So yes, it is suitable. Any other questions, sir?
No, sir. No questions.
No other questions.
Okay. Sir, thank you, sir. Thank you for your valuable presentation. And you can stop sharing, and you can give the answers for all the queries raised by the participants. Okay. Thank you once again on behalf of our college management and organizing team. We are really thank you for accepted my invitation with your busy schedule, sir. Thank you very much.
Pleasure to have joined and pleasure to have shared my experience with all the participants.
Yeah.
Thank you so much.
Thank you. Participants, now I'm ending the session. So the feedback link will be shared in the chat box. Okay, so please give your feedback. By afternoon, the session number 6 will be start by exactly 2:25 p.m. Okay, so the link, Zoom meeting link will be shared to your WhatsApp as well as to your mail address. Okay, thank you. Thank you very much.
Thanks.
Thanks. Yes, sir. Yes, sir. You can leave. Thank you, sir. Feedback. Okay, thank you. Thank you very much. I'm ending this meeting.